Alrighty, so somebody's asked me what would happen if you had a capacitor that was in two parts that were next to each other, and they had different dielectric properties in the insulating part between the two electrodes, the anode and the cathode. So this is a perfect excuse for a bit of electrostatics in a finite element solver. So I'm going to use FEMM for this because it's a planar problem, and FEMM is quite quick to set up for this sort of thing, and it's feature rich considering how easy it is to use. So you can download it from femm.info, and there's a good manual online. There's plenty of tutorials as well, but just to solve this problem we have new and electrostatics problem, and that will give us where we draw out the problem. So FEMM only does 2D, or I expect you could probably do 1D in it if you tried, but it doesn't do 3D. And it doesn't do transient either. It will only do magneto-electrostatic, thermal or circuit type problems, or time harmonic problems. So you can look at rotating machines, that sort of thing, by stepping through the different positions that you want it to use while applying frequencies of currents of a certain frequency, for example. So in this case, this is just a setup for the problem, and we'll have a look at how it's set up, and then I've got a couple that I've pre-solved already, which will give us some answers in a semi-realistic situation. Still not very realistic, but enough to demonstrate the answer to the question that was asked. So initially I'll set up a capacitor that's a meter square in area with a meter between the plates, and the plates will be infinitely thin and perfectly conducting, and the dielectric will be it will be a vacuum, although I'm going to call it air because air and vacuum are very, very close in terms of dielectric properties at low frequencies. So I'll start off by pressing tab, which will, with the point or node selected, will allow me to draw out the nodes. Usually you draw a little diagram to show what it is you want to draw on a bit of paper and know where the nodes are on planet, but since this is a reasonably straightforward, in fact trivial actually, example, I don't need to draw a diagram for this. So something at the origin, that's down here, so I'll just zoom out a bit and tab 1 meter, nothing, nothing, 1 meter, 1 meter, 1 meter. Then I'll make the two boundaries that are the electrodes by pressing they call them segments, but usually I would call it boundary because I'm going to put a boundary on this in a bit. Then I need to make a definition for the edge of the universe. In this electrostatics problem, we need to define some limit after which the mesher won't continue to mesh. We can't mesh forever and look at the field an infinite distance from these two plates. We have to make a decision about how much simulating we're intending to do. And the usual sort of rule of thumb is about 5 times the size of the problem. And of course you have to mesh all of that and then you have to solve it. And that's computationally sometimes quite intensive, but in this particular case we don't need to worry too much about it. It's reasonably easy to solve. We could just put one boundary line and explain to the solver that we want the electric field that touches the boundary not to pass through it, and for the electric field that does touch the boundary, electric flux, sorry, not electric field, that touches the boundary to be passed tangentially along the boundary rather than to penetrate through it. As it is, we can go one better, or a little bit better than that, and use it's an impedance match layer effectively, where we gently redirect the electric flux rather than force it in a way that's not particularly realistic. So my problem is about a metre in dimensions, so I have a 5 metre radius around that, which is ample. It's really probably a bit too much, but it doesn't matter. You can look in the manual if you want to know what the pros and cons of each mechanism of constructing the boundary, but I will leave it as is. Same goes for the number of layers. So this is my edge of it's inside of the universe, and this is outside of the universe. And if I do my simulation and I find I've got fluxes, electric fluxes outside of here, then we've got problems and something's not right. So I need to define that this is the anode and this is the cathode, because that's how I want it to be. And I need to say that inside all this lot is air. So the way I would deal with air is by going to materials. There's already a lot of stuff here which is to do with the boundary, but I can ignore that. Add a property, we'll call it air. And if you go to the table of, I'm not an advocate of RF Cafe, there's an awful lot of adverts on it. Sorry if you're the owner, but there are. You can see air is dielectric constant, the ER is a bit more than 1, but I think we won't die if we just call it 1. And it's the same in both directions. So having created that, I can then put it down with operate on blocks. I just drop it down, right click, space bar, and then I can tell it that it's air. And it knows that it's air everywhere, including between these two lines, boundaries. So then I can set up some conductors, and I can make anode, and I can make 1 volt on the anode, and I can make a cathode, and I can put 0 volts on the cathode. And then I can select the two things that I want to be conductors, or boundaries. So I right click, spacebar, sorry, not boundary, in conductor, anode, same again, in conductor, cathode. Then I should just be able to mesh it. Oh yeah, you have to save it. Save as. Then I should be able to mesh it. So it's meshed. And then I should be able to solve it and have a look at the results. And we're looking at a plot of the voltage at each grid point. So around the anode where I prescribe 1 volt, I can see that it's just about a volt, 9.5 times 10 to the minus 1, so that's nearest down at 1. And around the cathode, which I prescribed 0, is pretty much 0 volts. And in between we have this graded region where the voltage is dropping as we pass from one plate towards the other, which is what you'd expect to see. I might in fact go and change this a little bit. So I can go back now and maybe add some more points, because it will make it easy for me to do some of the processing that I want to look at the data. So we can go half 0 and half 1, just to put those 2 points in. I don't need to re-explain that both of these halves are the anode and both of these halves are the cathode. If you don't believe me, check, but I've tried this already to make sure the video runs reasonably smoothly, and I know it's okay. So I resolve it. Really, I don't. I do need to resolve, because I want it to include those dots. So I can choose my contour, and I can draw a line. And if I look at the voltage, sure enough, starts at 1, drops towards 0. So this is the position of the anode. The reason it says 0 is because I started that line up here and took it to down here. If I'd started the other way, we'd get a slightly different graph that displays essentially the same information. And it's not surprising, if we had different materials we would see this is not a straight line. Other thing I can look at is we could probably try to draw the vectors, but I suspect it won't draw very many vectors. Yeah, that's not very helpful. We will have a little look at that in a different model. How do I make those go away? No, there we go. We can ask it for the total energy that's stored by integrating across the volume. Well, I say volume. The volume because we are into the page as well. It's not much, but that's not very surprising because this capacitor is not very large, and the inner area of the plate and the distance between the plates is enormous. So that's how you would set up the simulation. If you want to look at the electric field, you can, either as a colour plot like this, or it looks fairly ugly. There is one thing I didn't do which I should have, which is tell it that this is all in meters, and that. Okay. Right. The reason is when I look at this, I want to run the numbers so that I'll get a volt per meter in the electric field, and I'll have 1 meter here. I'll prescribe 1 volt, so we ought to see a volt per meter. The only reason I do that is so that the numbers are easy for us to interpret and just go, oh yeah, that's how it ought to be. When you're setting up your finite element, doesn't matter if it's something trivial like this or if it's really complicated 3D magnetostatics problem for machine design or whatever it might be, RF heating or multi-physics, this, that, the next, doesn't matter. Always start with something you know the answer to, in order that your simulation, if you've buggered up the setup of the simulation, you'll pretty quickly realise that something's not right. If you ask it questions that you don't know the answers to, it will provide you with numbers and you'll believe them, and they might be complete garbage. So always ask it simple questions first until you're sure that the simulation is working. Then you can start to experiment on the things you don't know the answers to. So electric field we can look at in a plot like this, and that's not very interesting at all. Other way I can do it is by looking at the contour plot down here, and we'll the normal field intensity won't be very big. It'll all be tangential. The reason is we're looking tangential to this line, and the electric field around here will be a certain value, and around here will be a certain value. In between will probably be quite constant, but it will be changing across this region, whereas into the page we shan't see very much difference at all. But we look at the magnitude anyway. There we have it. So it's pretty much 1 volt per meter. If I took the average of this curve, I bet you it will lay about there. The reasons for the dip, I don't want to get into it too much at the moment, but that's what I'd expect to see for a cap that's got a volt on it and a distance between the plates of a meter. You should have 1 volt per meter, so that tells me things are okay. What else can we do? We can have a look at the equipotential lines. So this is in voltage effectively. So we're looking at around here, these lines are close to 1 volt, and as the lines go further and further from the anode, we are looking at less and less voltage. This will be about half. I think you can even press tab at this point. No. Oh well. I thought it might display the data under the mouse cursor, but clearly I need to read the manual a bit. And we'll get towards the area down the bottom. So that's how you do the problem setup, and you can see as well here how the boundary is redirecting this flux line, because it should just go on and on and on, but it's kept within the universe. We can't have any electric flux leaking out beyond this boundary. So that's how you do the setup and look at the data. It's not exhaustive. There are some other things you can look at as well, like the charge on the conductors, the stored energy and that sort of thing. But we'll have a look now at a slightly more realistic capacitor. Not very much more realistic. We're still looking at something that's about 1 meter across, and I'm going to vary the distance into the page by editing the depth in the problem setup. So that's the depth into the page. The simulator knows that there is a depth to this problem. It doesn't think it's a 2D problem. It presumes that it's just not changing in that third dimension. So we only need to do the maths on a 2D, and then we just essentially make believe the third dimension is there, and it saves us a lot of computational effort. So if you run the simulation for this one, I've already got it set up, so I just run. This is air, and the distance between the plates is 5 millimeters, and the plates are 1 meter by, at the moment, 4 meters in the direction into the page. And we can look at some data, and we could, if we wanted to, integrate for the stored energy, which is what I've been doing. And if you do it, you get an answer in joules. And if you recall, the stored energy in capacitor is half times the CV squared, where C is the capacitance and V is the voltage. And if I was to then go back, go into the problem, make that 3 meters, run it, look at the data, look at the stored energy, I would get a new value, and that value is a bit lower than the last one because it was about 3 point something. And I can keep going in this fashion and record set values. I don't really like Excel, but we're not really doing big data here. I've got 4 rows, so I think we'll survive. So the width is a meter, the depth is a meter. That's the depth into the page is a meter, and I have got the stored energy for this particular set of situations, and these are the two that we just looked at. 2.7, let's just check, shall we? Oops, wrong one. 2.69, fair enough, that's quite close. I expect if I got an extra digit, it's, yeah, 269, so it's the same. And from that I can work out the capacitance. I know the voltage is a volt because that's what I determined it as when I set up the conductors. And I know that I know what a half is, so I can work out the capacitance given the stored energy. So I can do that, and it turns out I just divide the stored energy by half or multiply it by 2. I know what the area is because I just multiply the width and the depth. I know the separation distance, that's just the distance between the two conductors, and I set that when I drew out the model. There's no particular reason why I chose 5 millimeters, I just wanted something that was considerably smaller than the width and the depth. The reason I wanted that is because the question that was asked that led to this video was about if you can still use the parallel plate capacitor formula when you have a capacitor that has a dielectric of, say, air over here and then a different dielectric over here, and how would it all pan out. So I just wanted to make sure that the parallel plate approximation will be valid-ish, and the key thing that determines that is there is not too much fringing fields, which is the fields that get at the edge, compared to the fields where the plates really are parallel, and they appear to be parallel for quite a long way out. If you're in the middle looking outwards, you see a lot of parallel plate, whereas if you're on the end, you see fringing. So I want to see a lot more middle than I see end, and then parallel plate approximation should apply. So if I run this is E naught ER, ER for air is 1 in this case. I know air is not really 1, but I said it was in the when I set up the model. And then we do the area divided by the distance between the plates. So we see the values here and the values here, and they are in pretty good agreement. In fact, there's barely anything in it. I take those as it matches, more or less. So that's the case for just the air, so this looks like a good parallel plate cap. We can look at another simulation as well, where I've split the regions. So if I zoom in now, this is otherwise identical simulation to the one we just did, but there's a tiny little bit at the end there. See if I can go in a bit more. There it is. And again in the middle, which is just off the left here. So this region now is made of FR4, which is the stuff that PCBs are made of. Well, the stuff that PCBs that work at low frequencies are made of. And if I go into my listing from RF Cafe, FR4, and I choose the low res version only because it gives me a higher dielectric constant. FR4 is really only good up to about, I don't know, a couple of gig. You wouldn't want to go much higher than that because you start to get dipole loss, and the board effectively is getting hot, and all your RF energy is not going where you want it to. It's going in your board and making your board warm. So if you're going to high frequencies, people usually use Rogers. Well, the Rogers is the manufacturer of lots of high frequency boards that are made of a variety of other things. And you can see if you look at the Rogers, this is just one particular one. It's got half the dielectric constant of the FR4. Really, the ER is not terribly important. That's the real part, because the epsilon actually has real imaginary parts. The bit that deals with the loss is really the relative size of the two of them. But we needn't get into that now, because this is not really an RF thing that we're looking at. Anyway, I picked this because I can. It's the sort of thing that you'd have lying around the lab if you wanted to try and make a capacitor and put something in the middle to see the dielectric varying. So the way I've set that up is to go into the properties and make a new material. And the material is FR4, and if I look at it, I'll just put it's isotropic properties as well. It's got the same ER in both directions, the X and Y. And then I'll just drop that down. Beyond that, everything else is the same. So we can run it and view it. And if we zoom in, we can have a little look at the field. Sorry, not the field, this is the voltage distribution. But one thing I can do is select the region which includes the air between the plates and the air in the rest of the universe, but not the FR4 material. And I can look at the stored energy, and it will be some value. Doesn't really matter what it is. Then I can choose just the FR4 region and look at the stored energy there. And it's considerably... Okay, I said something that it's only a half truth there. The energy is not stored in this region. The energy is stored as electric potential. And there is an electric flux in this region, which is the expression of that stored energy. Really, it's because there is charge on the plates, and the charges are attracted to each other, and that maintains the charge there. And the charge is held across a voltage, and that voltage represents the potential for the work to be done. The charge must flow to do the work. So the energy is not stored in the FR4. That's not. I did say that, and it's not quite right. But we can see the stored energy, which is enclosed in this volume, is about 2 times 10 to the minus 9 joules. And if we look back at the stored energy in the air enclosed volume, it's half an order of magnitude less. And of course the ER here is 1 and the ER here is about 5. So if I was to go through all the rigmarole of setting up the depth of the problem again and making an Excel sheet, like this one, we could have a little look at the stored energy in the air section and the stored energy in the FR4 section, and we can then compute what the capacitance is due to the air section and the capacitance is due to the FR4 section. And then we can compare that with the parallel plate formulation for the two regions, not forgetting of course that here the area has gone down by 2 because this parallel plate capacitor has been cut in half, and only half the area has now got air between it, and half the area has got FR4 between it. Oops. And having done all that, we can see there's very reasonable agreement between the air capacitance and the air parallel plate formulation and the FR4 capacitance and the FR4 parallel plate formulation. In other words, making half this this capacitor out of with FR4 dielectric doesn't ruin your parallel plate approximation, provided that the distance across the capacitor is great compared to the fringing effects that you would get at the two ends. As long as that applies, then it'll be okay. If you want the total capacitance, you'll sum that value and that value to give whatever that gives at this particular separation, at this particular depth into the plane. And if you sum that and that, you'll find that they add up very much the same as that and that. There's not much difference to it really. You can see that this is a 2.1 e minus 9. That's quite a big difference actually. Oh, that's the stored energy, that's why. Oh, thought I was talking rubbish for a second. Wouldn't want that to happen. Yeah, 4.339, 4.337, both raised to the minus 9, and 8.85 to the minus 10, and 9.09 to the minus 10. So that plus that should equal that plus that. And if that is the case, then we can take it as read that it's okay to use parallel plate formulation with a capacitor where you have two dielectrics, each taking up a certain proportion of the area of the capacitor. If this region was very, very small and occurred only near the end, this parallel plate formulation would break down a bit. It wouldn't apply properly because the fringing fields, which is if you look at the result here, don't know how dense our mesh is. We might not see it very well if I zoom in. Try zoom in some more maybe, and some more. See if we can see the atoms. Yeah, okay, so in this region you've got very sort of linear graduation of the voltage, whereas as we get towards the end, because there's no capacitor here, or plate here, the electric flux is not bleeding as such, but there are these fringing fields which exist because the geometry has changed, and our parallel plate assumption doesn't take account of this bit. It pretends that the flux just stops at the edge here and there's nothing coming out the side. And you can see that actually the bit inside the capacitor which is not got parallel lines of voltage gradient is actually quite small. It's only the width of the mouse at the moment compared to the size of this thing which goes right way off the left hand side of my screen. So we shouldn't expect to find a big error. If the FR4 region was quite small and it was in fact large compared to the fringing distance, then we'd start to worry about whether this applies or not. Anyway, in practice you don't make capacitors that are a metre square, and you don't really make capacitors that only have two electrodes. There are two electrodes, but they are constructed in an interdigitated fashion so that you can have more than one. You can have anode cathode with a dielectric, and then you'd have another layer of dielectric, and that would have an anode, dielectric cathode, dielectric anode. And in the case of the aluminium electrolytic or similar ones, you then roll those up to make a cylinder and put a wire on each electrode. So you end up with two wires, one for all the anodes and one for all the cathodes. And it's the same sort of thing for even sort of a microwave ceramic capacitor. Has an interdigitated structure. It's not rolled up into a coil type arrangement because that provides a lot of strain inductance. But it allows you to make quite a big or a relatively large capacitance in the smallest volume that you can get away with, which is important because space is a premium in electronics design. Right, if you've got any questions you can drop me an email.